For the second part of this short course, we're going to talk about functions of matrices and functions of structured matrices. So my slides were for the whole course, so let's jump to the ones we need. Okay, there we are. So part 2, functions of matrices. So, I think all of us are already familiar with some examples of functions of matrices. Perhaps one of the best known is the exponential of a matrix, and Guillaume mentioned it yesterday in his course, giving us an example of where it is used. We've certainly met it, for instance, in the solution of certain kinds of differential equations and many other applications. We'll see one of these in the following. So let's recall the definition of function of a matrix. So there are different possible definitions. One of these is based on the diagonal or Jordan form of a matrix. So let's suppose first, for simplicity, that our matrix A is diagonalizable. So suppose it can be, let me see if the pen works. I'd like to scribble a little on my slides. There we are, okay. So suppose our matrix has an eigenvalue decomposition. So A is factored as a certain matrix, invertible matrix X times the diagonal matrix of eigenvalues times X minus 1. So A is X times lambda 1, lambda 2, lambda n, X minus 1, okay. And suppose we choose a function, real or complex, which is well defined on the spectrum of A. So here we just ask that f of lambda j is well defined for every lambda j. In this case, the function of A, f of A, is defined as x times f of the diagonal matrix, which means the diagonal matrix that has the functions of the eigenvalues as diagonal entries times x minus 1. Okay, so basically, I look at my matrix, at my linear application, in the basis where it's diagonal, and there I apply the function separately in each direction to each eigenvalue. And I go back to my first reference system. This definition can be extended to any square matrix using the Jordan decomposition for the case where the matrix is not diagonalizable. So in this case, while the definition has been more involved, so suppose we have a Jordan decomposition. So instead of a diagonal matrix, we'll have a block diagonal matrix where, so J is made up by these blocks J1, J2, Jm. So what we want to do is again to say that f of A is x, f of j, x minus 1. What is f of j? So if j is block diagonal, it's safe to assume that f of j is the block diagonal matrix made up of the functions of the blocks. What is f of a block? Well, it's defined like this. So suppose jk is a Jordan block of size nu times nu with associated eigenvalue lambda, and then f of jk is this upper triangular matrix, which has on the main diagonal f of lambda, and then f prime of lambda, f prime of lambda over 2, and so on and so forth. Okay, so in this case, we have to assume, in order for this definition to be well posed, we have to assume that f is defined and sufficiently and differentiable a sufficient number of times on each eigenvalue. Okay. there are other possible definitions. One of these uses a Taylor series. So if F has a Taylor series expansion like this, so sum of ak z minus z0 to the power k, an expansion around about z0, with a certain radius of convergence r, and if we ask the spectrum of the matrix to be contained in the interior of the convergence disk, or it can also be on the boundary, but we have to be careful in that case, then f of a is well defined, and its expression is exactly what you could expect. So f of a is the sum of ak times a minus z0 times the identity matrix to the power k. And the converse is also true. So if f of a can be written by means of the Taylor series of f of z, then the eigenvalues of a must satisfy these conditions. So they must be contained in the convergence disk, of course. And yet another definition, which is very elegant, is based on the Dunford-Cauchy integral formula, which is a generalization of the usual Cauchy formula for evaluating a function in the complex plane. So this definition says, so suppose as usual that A is an n by n matrix, and suppose F is a function that's analytic inside a closed contour gamma that encloses the spectrum of A, right? So we have the complex plane, and in the complex plane we will have the eigenvalues of a matrix, and the this contour gamma must be something that encloses the eigenvalues. So it could be something like this, for instance. So we want the eigenvalues to be in the interior, okay, of the region whose boundary is gamma. In this case, f of a is defined as 1 over 2 pi integral of the contour gamma of f of z, zi minus a to the minus 1 dz. Okay, this is clearly a generalization of the usual Cauchy formula. And so if you suppose that A is diagonalizable, you can easily see how, you can easily get an idea of how this works and why it is related to the definition we had before. Because if you assume that A is equal to, what did we say, x d x minus 1, for instance, and we replace this in the formula, what we get is the integral over gamma of f of z, z times identity, minus x d x minus 1 to the minus 1 dz. At this point, the identity can be written as x minus 1. And so basically we can take these matrices x and x minus 1, this conjugation, and put it outside the integral, okay? So what we're left with is something like this, x times the integral of f of z, zi minus d minus 1, dz x minus 1. And here we have the inverse of a diagonal matrix. So it is again a diagonal matrix whose entries are the inverses, okay? And so what we get is basically a diagonal matrix where on each diagonal entry, I have applied the usual Cauchy formula about an eigenvalue of our matrix. Okay, so we get exactly the same expression we had for the diagonal form. All these definitions are essentially equivalent, where essentially means there are slightly different hypotheses on when they work and when they don't work, but assuming that all these hypotheses are satisfied, then all these definitions give us the same results. And more definitions are possible, for instance, using interpolation polynomials, but we won't go into this. There's a famous, very, very nice and comprehensive book by Hayam on this topic, functions of matrices. Okay, so let's look at some examples now. So, well, one first example of matrix function is, of course, the matrix inverse. Okay. Another one is a matrix exponential, as we said, but we can also compute trigonometric functions of matrices, like sine or cosine of a matrix. We can also compute discontinuous functions of matrices. For instance, a sign matrix or a step Heaviside matrix. And this is actually useful in some applications. For instance, you probably remember from the examples yesterday in the introductory part, there was a picture of the discretization of a Hamiltonian operator for a certain hydrocarbon chain, right? It was that picture with the entries of the matrix depicted in black and blue and yellow. Okay, it was an approximate band structure. In some problems in electronic structure computation, one actually needs to compute a step function applied to such a Hamiltonian matrix. And this is a bit tricky because you have to be careful that the discontinuity of a function falls in a place where there's a gap in the spectrum of the matrix. Otherwise, a function is hard to approximate. And it's also hard to prove many useful properties of the matrix. So it's possible to compute discontinuous functions, but we have to be careful. The matrix square root is another example of function we can compute. And here we need extra care because the square root is a multi-valued function. So in order to compute so-called primary functions of our matrices, we need to be sure that we're taking the values of the square root from the same branch. Okay. So for instance, with our square roots of the identity matrix, you could put some minus ones on the diagonal if you like, and the square is still the identity, but that's not a primary function. In many applications, we don't necessarily have to compute the whole matrix f of a, but we might just want to compute the action of f of a on a vector. Okay? Or sometimes we might just need to compute selected entries of f of a. Maybe I just want f of a ij for a certain choice of the indices. Or sometimes we need functions of the entries of A, like the trace. And depending on what we're trying to compute, different methods are available. Okay, so now this talk is about structured matrices. So the natural question that arises is, what can we say about functions of structured matrices? And in particular, we can ask, first of all, if A is structured, is f of a again structured? So the answer is, in general, no. However, in many cases, it turns out that f of a retains an approximate structure. So it does not have exactly the same structure as a, but it's close to having the same structure. And this can be useful in applications. Of course, we have to characterize precisely what we mean, what we say approximate structure. And another question, of course, is how can f of a be computed efficiently knowing what the structure of A is? So how can we exploit the structure of A in order to compute f of A? And so both questions are topics on which there is active research being conducted. Some partial answers are available, particularly for functions of banded and sparse matrices. We'll talk about this, especially about the preservation, approximate preservation of a banded structure. There are results on functions, namely on the exponential of triplet matrices. We're not going to talk about this, but there's vast literature on this. It's a very fascinating topic. And there are also results for certain functions of quasi-separable matrices, and we'll say a few words about this. Okay, so let's start with the second question. So how do we compute functions of structured matrices? So let's first take a look at the usual unstructured ways of computing f of a, and then let's see if the main operations we perform in the course of these algorithms can be reframed in a structured way. For instance, usual methods of computing f of a include rational approximations. Okay. For instance, take the matrix exponential. One of the most widespread ways of computing the matrix exponential, the one that's implemented in MATLAB, for instance, is the so-called scaling and squaring method. And the way it works is that it takes a matrix, it scales it so that it has norm bounded by one, by a reasonably small number, and then it applies a rational approximation of the exponential functions. In practice, there are families of rational approximations available for the exponential function, and what turns out to be the most, the best suited one is a certain approximation, rational approximation with degree 13. And then we scale back the matrix to the norm it's supposed to have. Another approach is that of rational iterations. So we can apply an iterative method where each iteration is of a rational nature. For instance, Newton iteration. This is what the Newton iteration looks like for the sine function. Okay, it's basically Newton applied to the equation that defines the fact that the behavior of the same function. And other methods belong to the so-called family of Krylov methods. So, but in particular, these are methods that rely on products, matrix vector products, A times a certain vector V, and so they're especially well suited with for the case of matrices for which the matrix vector product is computed easily, is computed in an efficient way. And these are mostly used for approximating the action of f of A on V. So I see there are questions, so maybe we can have a quick break to answer the questions. So how did you choose the mu? Where is mu? Wait. Can you please tell me on which slide is this? No, okay. The size of the Jordan block. Yes. So I did not choose it. It's a size of the Jordan block we're working on. So if A has a decomposition, okay, Jordan decomposition, each block has a certain size. Okay, that depends on the structure, on the properties, the spectral properties of the matrix. And so we need to define what it means to compute f applied to each of these blocks. And so here I'm denoting as nu the size of the block. Okay, and so I need to compute at least nu minus 1 derivatives of my function on the eigenvalue. So the function needs to be at least differentiable at least nu minus 1 times on eigenvalues that have associated blocks of the size. Okay. So yes. Frederick Chizak, what are these notions of sine, heaviside? Yes. So for sine and heaviside, perhaps the easiest way of seeing this is by taking the definition based on the diagonal or Jordan form. Let's take the diagonal form. Maybe that's easier. For instance, the sine function. If we assume that A, so I didn't take any hypothesis here on A, but for the sine function, it's perhaps easier if we assume that A has real eigenvalues. So suppose that A is, say, Hermitian. Okay, so it has real eigenvalues. So A is x times lambda 1, lambda n, x minus 1, where all the lambda j's are real. And then sine of A is x times the sine, so 1 or minus 1, lambda 1, sine lambda 2, and so on. So really the sign of the real number, okay, times x to the minus 1. Okay, this of course has a discontinuity in 0. And for the Heaviside function, the principle is basically the same. So the Heaviside function is, well, it's usually taken, let's see if I can change the color. Yes. It's usually taken to be something like this, right? So it's 0 on the negative real axis or up to a certain real number. And then from then on, its value is 1. Okay, so we have, again, a jump discontinuity. Okay. And we can apply this to a matrix. I hope this answered the question. Okay, slide 64. Is there any problem if one of the eigenvalues lies on the contour? Oh yes, absolutely. When I say encloses the spectrum, I mean strictly. So we are sure that this inverse is always well defined. So I want the eigenvalues to be in the interior of this portion of plane whose boundary is gamma. Okay, very good. So let's go on. Yes, exactly, strictly encloses. So we don't want the eigenvalues on the contour, otherwise you never know. You might not be able to define the inverse. Okay, so about the computation of functions of structured matrices, so what we were saying is we can just take a standard method for the unstructured case and adapt it to the structured case when it is based on operations we can perform efficiently for structured matrices. Okay, so as long as our method, like the ones I listed here, relies on matrix inversion or on matrix vector product or on a small number, bounded number of matrix sums of products, we can compute f of A with A structured in an efficient way. Just employ the structured versions of inversion, of sum products, matrix vector multiplications, and so on and so forth. However, one can also tailor these methods specifically to the structure one is working with. One interesting case emerges in the case where the method we're using can be framed as a task of solving linear systems. For instance, let's take again the definition of matrix function based on the Cauchy integral. Okay, I'm always forgetting the i's here, sorry. So if we want to compute f of A times V, so what we have to do using the Cauchy definition is to compute the integral on a suitable contour of f of z times the resultant zi minus a to the minus 1 times v. Okay. Now, if so, each of these expressions is the solution of a linear system, right? Where the coefficient matrix is a diagonal shift of the matrix A, basically. So when we discretize this expression in order to evaluate it numerically, So we apply some kind of quadrature rule, some kind of numerical integration rule to this integral. We end up with a finite sum. So I didn't say what are the possible values for k, but it's usually a finite set, like k goes from, say, 0 to a certain n of weights times the value of f in the nodes. I have to choose weights and nodes for my quadrature formula, right? It could be the trapezoid formula, for instance. So times f of zk times, and there we go again, the solution of this linear system of this form. Okay, so here we have this xk, that is a solution of the linear system with matrix zk times identity minus a. And the right-hand side is our vector v. Okay, so in order to evaluate this formula, I need to solve many linear systems, as many as the number of nodes I take on my contour. Many linear systems where the coefficient matrix is always different, but there's a close relationship between all these coefficient matrices because they're all diagonal shifts of each other. So the question we can ask is, certainly if our matrix is structured, we can solve, if our matrix is structured and if its diagonal shifts are again structured, we can solve these systems in an efficient way. But can we avoid starting from scratch each time we solve a new system, and instead reusing part of the computations we have already done and find an efficient way of solving all these systems together instead of each of them independently? The same question arises with other rational approximation formulas for certain specific functions, which can be, well, expanded in a rational series, where, again, if you want to compute, if you want to approximate f of a times v, you end up with a formula where the bulk of the computational effort is solving many linear systems where the matrices are diagonal shifts of each other. So let's take a look at how this can be done in the quasi-separable way, in the quasi-separable case, since we are mostly dealing with quasi-separable matrices in these talks. So as we said, our problem is we have this set of shifted linear systems. So we call sigma j the shift, the diagonal shift of the jth system. We assume that A is quasi-separable, and, well, the sigma, of course, are numbers. We are complex numbers, and the bj's, the right-hand sides, are vectors. They can be the same for all the systems, or they can change. So we want to exploit both the quasi-separability of A and the shifted structure. Note, by the way, that adding a diagonal shift to a quasi-separable matrix gives us, again, a quasi-separable matrix. But the representation changes every time. So if we were to apply the naive method, the naive structure method, we have to start again for every system. Okay, we expect, of course, all of that complexity, but what we will expect is to do better than just applying the structure method to each system. So in the quasi-separable case, the main idea relies on the way the QR decomposition works for quasi-separable matrices. So if I have a quasi-separable matrix M and I want to factor it as Q times R, so Q is unitary and R is upper triangular, but there are methods for doing this with linear complexity, and then you can use these computed factors to solve a linear system, obviously. And the way this QR decomposition can be computed is through repeated factorizations that give us this form. So this product, V times U, where U and V are banded unitary matrices, this product is the unitary factor Q. And then we have the upper triangular factor R. Okay. So what is interesting here is that Q is decomposed as a product of V times U, where V only depends on the generators of the strictly lower triangular part of M. Okay. So this is my matrix M, this is the main diagonal of M. The Q factor, the computation of the Q factor is broken down and the computation of V and U. U depends also on the diagonal, but V only depends on the strictly lower triangular part of the matrix. It does not involve the diagonal. So when we compute the QR decomposition of this collection of matrices obtained by diagonal shifts, the V matrix is always the same for all the matrices. And so we can reuse it. Okay. So for a shifted quasi-separable matrix, A plus sigma I, the QR decomposition, the quasi-separable QR decomposition, is made up by a unitary banded matrix V, which is the same independently of sigma, and then another unitary banded matrix U, which depends on sigma, and an upper triangular matrix that depends indeed on sigma. And so we can design an efficient algorithm where the complexity is halved with respect to the sequential structure method, where you solve the system from scratch every time, because we reuse the computations we have made for the matrix V. So let's take an example to see how this works. This is an example taken from a paper by Simoncini. So here we have a matrix of size 2500, which is obtained from the discretization of a certain differential operator on the unit square with zero boundary conditions. Okay. So what we obtain is a banded structure. Okay. So this is certainly a quasi-separable matrix. Here we have a close-up zoom of a little piece of this matrix. So what you can see, there's a main band here, and then there are two secondary bands here at distance 50 from the main diagonal, because this depends on the chosen discretization, okay, with 50 points in each direction. Okay. So the quasi-separable structure of this matrix can be seen in two ways. We can look at this as a usual quasi-separable matrix with quasi-separable order 50, because 50 is the bandwidth. Okay. Or we can also look at this as quasi-separable matrix with block structure. So a block quasi-separable matrix with blocks of size 50. In that case, we have a tridiagonal structure. Okay. So what we want to compute here is the square roots of this matrix times a vector of all ones, because that's what the problem asked. And what we need to do is to discretize this, the expression of the square root so that it can be computed using solutions of linear systems. So we want a kind of expression like this. The square root of A times B should be the sum of a K of a weight times the solution of a linear system obtained from a diagonal shift of the matrix A and with vector given by AB. Okay. I see a question by Xavier. If A is structured, for instance, quasi-separable, does f of A, or say square root of A, keep some structure? This is a very interesting question. And the answer is, in general, no. However, an approximate structure is preserved. And I'll say something more later in the talk. So I'll answer this later. But there is no, generally speaking, there is no exact preservation of the structure. There's an approximate preservation of the structure. Okay, so how do we compute this rational approximation for the square root of A? Well, there are many ways of doing this. There's a very interesting paper, very famous in the rational approximation field by Heer, Hayem, and Trefethen. This is known as the 3 Nick paper because the 3 authors are all called Nick. This paper proposes several methods for the rational approximation of certain functions of matrices, like the square root or the logarithm. It's concerned in particular with multi-valued functions. And the main idea is to take the region of analyticity of a function and map it conformally to an annulus, and then apply a quadrature rule on the contour of the annulus. Okay. They developed several methods depending on what kind of singularities the function has. So in particular, for the square root, there are 2 of these methods which are appropriate. One of these is developed specifically for the square root, and the other one is a bit more general. It's developed for all functions that have a branch cut on the negative real axis. Okay, so well, the square root certainly satisfies this property, and the convergence of the quadrature rules is geometric. Of course, the convergence rate will vary depending on, well, on the properties of functions and so on, but also depending on the method that's being used. So, of course, for the square roots, this method 3 is more efficient. So the convergence rate is better, but there is still a fast convergence. So this approach gives us a rational approximation where we can apply this efficient solving of shifted quasi-separable systems. And here are the results from this efficient implementation for quasi-separable matrices. There are several approaches we can take. Well, one of these is the classical backslash solver in MATLAB. So this is basically the pivoted Gauss method. We can apply the structure solver just described with blocks of size 1 and quasi-separability order 50. Okay, so we take the matrix as being banded with bandwidth 50. Or we can take the quasi-separable structure with blocks of size 50, and then the quasi-separability order will be 1 because the matrix is blocked by diagonal. And in all cases, we get essentially the same results. So we're happy with the accuracy of the method. Here we can see a relative error on the solution with the 2 methods I mentioned from the 3 Nick paper. So with method 2, method 3. So we can see that the convergence with the number of terms in the expansion is quite faster in the case of method 3 because, as we said, it's specific for the square root. And these relative errors are computed in 2 norms with respect to the result obtained by the standard MATLAB function that computes the square root of a function. This is based on the Schur factorization of the matrix, so a completely different approach. Here's another example that comes from a matrix equation. So the matrix equation we deal with is a Sylvester type matrix equation that is obtained by discretizing a Poisson equation, a Poisson differential equation. Okay. If we have this equation on a rectangle, so the rectangle has sides A and B. Okay, this is the domain where we study this equation. For the discretization, we have to take nodes on this side of the rectangle and nodes on the side. So suppose we have NA nodes here and AB nodes here. And then we have a grid, right? When we discretize the differential operator, and we end up with this matrix equation, AX plus XB equal F. All of these are matrices. X and F have size NB times NA. A and B are square of sizes NB times ND and NA times NA, and they are symmetric tridiagonal. The entries are actually -1, 2, -1, 2 septuplets. Okay, that's kind of full. Why is this related to a problem? Because how do we solve such a matrix equation? So there are several approaches. One of these involves vectorizing the unknown matrix X, so transforming into a vector where we put all the columns of the matrix one under the other, and then we solve a linear system with a bigger matrix. But another approach that's perhaps more convenient for us is to use the Bartas-Stewart method that relies on a Schur reduction of the matrix B. So Schur reduction means the following thing. If you have a square matrix, you can decompose it as unitary times upper triangular times U star, okay? So T is upper triangular. If we apply this is called a Schur decomposition. If we apply this Schur decomposition to the matrix B, which is symmetric, then the triangular matrix here has to be symmetric, and so it has to be diagonal, okay? So basically what we get is the eigendecomposition of B. Now, if we replace this expression in our matrix equation, what we get is AX plus X times UD U star equal F, okay? And if we multiply everything on the right by U, we obtain a new equation, new matrix equation, where the new coefficients are A, a diagonal matrix, and F times U. And the new unknown is X times U. So here we have a matrix equation with this diagonal coefficients. And this means that solving this matrix equation amounts to solving a collection of shifted linear systems, where the matrix is quasi-separable, because it's what we have are shifts of the matrix A, which is banded and therefore quasi-separable, okay? So let's take a look at the relative errors we have applying our structure method. And as we can see, the results are very, very close to the exact ones. So we're happy with the experimental stability of our method, and we're also happy with the complexity, which is halved, as we said, with respect to the sequential method. Okay. So we cannot hope in this case for an asymptotic improvement, but we can improve the constant in the expression for complexity. Okay, so all these errors are close to the machine epsilon, so we're happy with the results. Now, what about, so this was for giving an example, an idea of how we can compute functions of structured matrices in the quasi-separable case. As we said, we don't mention the displacement structure case here. Now let's move on to the other question, which is also related to what Xavier asked, which is approximate structure preservation. Okay, so is what can we say about the structure of functions of structured matrices? So we're going to talk about two cases. One that we will see a bit more in detail, which is the case of banded matrices. So what can we say about functions of banded matrices? Are they banded? And the other one's a bit more involved, but I'll say something at the end. What about functions of quasi-separable matrices? So there's a question, how do you measure the error? The error you mean in this table? Yes, so in this table, I measure the error as the 2-norm relative error with respect to the solution obtained by a standard solver. for the matrix equation. By standard solver, I mean a solver that solves this problem. So the usual way of solving this matrix equation is rewrite the matrix X as a vector and turn the matrix equation into a linear system with a bigger matrix A. And then, so the size of A is a product of the number of discretization we have on each side of the rectangle, okay? So we can apply a standard linear system solver for this and obtain good results. We'll take this as our exact result. And then we apply our structure method with the Bartos and Stewart approach, compute the solution, and then compare it to this one, compute the relative error interval. So this is a forward error. Okay. Good. So what about structure preservation in functions of banded matrices? So in general, functions of banded matrices are not banded. However, they have an approximate banded structure, meaning that functions of banded matrices exhibit a decay behavior. So the magnitude of entries, of off-diagonal entries, tends to decrease very quickly as we go far away from the main diagonal. Let's take a look at an example. So suppose A is a banded matrix, and we want to compute its exponential. Okay. So B is a full matrix, but it can be well approximated by a banded matrix. And we'd like to characterize this off-diagonal decay behavior so that we can give accurate estimates on where we can truncate the matrix in order to obtain a good banded approximation of f of A. Okay. So here's a picture. This is a plot of a banded matrix. Okay, so everything here is 0. Okay, and here I have the band. We're just taking just random. Okay, then I compute the exponential of this matrix, and what I get is this. So I have to say here it looks like these are zeros, but they're not. They're small numbers. So what you can clearly see is that the matrix has clearly non-negligible entries around the diagonal, but as we go away from the diagonal in this direction, the magnitude of the entries decreases very quickly. And so if we take a banded approximation of a matrix, for instance, with a band like this, the error is given by the norm of these pieces, and this is small if we take the band large enough. So the question is, how large should this band be taken? In other words, can we describe this decay behavior in the entries of the exponential of a matrix? So what we'd like to do is to find decay bounds that are uniform with respect to the size of the matrix, and it can be characterized in terms of a few simple properties of the matrix. So what are applications of these of this idea? I'd like to show you one that's related to network analysis. So applications, of course, are abundant since the matrix exponential is found very often in applications. But one I would like to show that's also related to the introduction we saw yesterday. You remember we saw that graph with the Renaissance families in Florence, right? One application is related to network analysis. So let's open a short parenthesis and say a few words about this. So we want to study networks. Networks are modeled by graphs. Okay, so networks are made up of objects think users, for instance, of a social network, for instance, and objects which are related by edges, which are joined by edges. So users who are related by, for instance, friendship links. So the kind of graph we're going to use here is a very simple model. It's an undirected, non-oriented graph. Connected, simple, meaning unweighted, undirected, and no loops. Okay, so say something like this, I don't know. For instance, this could be such a graph. I don't want loops. A loop would be something like this, an edge that starts and ends at the same node. So undirected, no directions on these edges, and unweighted. So all the edges have the same weight. We don't associate a number to the edges. So to this graph, we can associate an adjacency matrix, meaning we label the nodes, we give names, 1, 2, 3, 4, 5. And then we build a 5 by 5 n by n matrix where entry ij is 1 if nodes I and j are connected by adjacent, connected by one edge, and 0 otherwise. So for instance, here on the first row, we have that 1 is not connected to itself. Actually, all the main diagonal will be zeros because we don't want loops. 1 is not connected to 2, but it is connected to 3. It's not connected to 4. It's not connected to 5. Okay. And then for 2, we have that 2 is not connected to 1. It's not connected to itself, but we have 1 here and 1 here and 0 here. And 1 here, and so on and so forth. You get the idea. So since the graph is undirected, this matrix is going to be symmetric. Because node I is connected to node J, if and only if node J is connected to node I, J is adjacent to node I. Good. Now, it turns out that functions of the adjacency matrix can give us useful information on the properties, on the behavior of a network. So the main property on which relies this relation is the following. If we take a power, kth power of the adjacency matrix, then the entry ij of this kth power counts the number of walks of length k in the graph that connect node I to node j. Okay? So by a walk, I mean an ordered list. So it's what the name says, an ordered list of nodes such that successive nodes are connected, are adjacent. Okay, so it's really a walk on the graph. Of course, there can be repeated nodes. And the length of a walk is the number of edges that form the walk. So the number of nodes in the list minus 1. Okay, and it turns out that if I want to count the number of walks of length k that go from I to j, all I have to do is to take the kth power of A and look at the entry ij. This is easy to prove, for instance, by induction. Okay, if you look at the case k equal 1, that's the adjacency matrix, the definition of the adjacency matrix. And then if you write k to the a to the power k plus 1 as a to the power k times a, you will see, looking at the way the matrix product works, that you're actually counting walks of length k plus 1. Okay. So is this matrix unique? Oh, yes, unique, and it's uniquely defined. So if you have this, if you fix your graph and fix the labeling of the nodes, so you decide what name you give to the nodes, okay, this labels 1, 2, 3, 4, 5, then the matrix is completely determined. And vice versa, if you have such a matrix of ones and zeros, you can build the corresponding graph. However, if we, so it must be observed that relabeling of the nodes, changing the names of the nodes, of course, does not change the structure of the graph. So it's basically the same graph. And we're labeling the nodes corresponding to applying a permutation, conjugating this with a permutation. Okay. So the answer to is this matrix unique? Yes, if you fix the labeling. No, it's unique up to permutations if you can change the labeling. Yes, in real problems, you might need to relabel nodes. And in this case, you need to apply permutations on the matrix. And we'll do that in a moment. Yes. Okay. Good. So why are we interested in the length of walks on the graphs? Because in the network analysis community, one of the most asked and analyzed question is, how can we quantify the importance of nodes? Think ranking problems. For instance, you have web pages, you want to rank them. And how can we quantify the connectedness of two nodes? How well connected two nodes are? So there are many possible answers. There's a huge literature on this. But one possible approach, which is known as subgraph centrality and communicability measures, relies on counting walks. So for instance, let's take the centrality problem. Centrality means importance of nodes. I want to compute a score for each node that tells us how important that node is. That's called a centrality measure. One way of doing this is saying, well, I look at my nodes and I look at the walks that start and end at that node. And my point of view is that if that node is important, then there will be many such walks that start and end at that node. And clearly, short walks weight more and more important than long walks. So what I can do in order to quantify this, this notion of importance is to count the number of walks that begin and end at a given node, and sum their numbers, but with a weight, because I want long walks to weight less than short walks. So I can, for instance, choose a factorial weight. So what I want to do is to count the walks that begin and end at node I, where each walk, so the number of walks of length, of a certain length, is weighted with a factor 1 over the factorial of the length. Okay. How do I do this? Well, I use the property we saw before. So I use the powers of the adjacency matrix, right? So what is C of I? Walks of length 1, there are none, of course, because if I want to go back to my node, I have to have at least length 2. So let's look at walks of length 2. These are the diagonal entries of A squared, right? Weighted with a weight 1 over 2. Then, so this is the number of walks of length 2 with a weight. Okay. Then I want the number of walks of length 3. And so I take the third power and the ith diagonal entry. Again, weighted with 1 over the factorial of the length. Okay, so this is the number of walks of length 3. And then this is the number of walks of length 4, and so on and so forth, right? Very good. Now, you will see that this starts to resemble very much the Taylor expansion of the exponential function, right? At this point, we can also observe that we could add here the ith diagonal entry of A because it's 0 anyway, right? So it doesn't change the expression of C of I. Good. And now in order to have the Taylor expansion of the exponential, what is missing is a 1, right? And we can add a 1 if we consider that usually these centrality measures are defined in order to establish a ranking of the nodes. So we're not exactly interested in the value of the centrality, the value itself of the centrality, but we're more interested in the ranking of the nodes, and so how the values of centrality are related to each other, which is larger, which is smaller. Okay, so if we add 1 to all the centrality scores, this is not going to change our ranking. So we can add a constant. So this is the sense of the symbol. Okay, I can add a constant to my centrality score because it doesn't change the ranking. So I add a 1, and what I obtain now is exactly the Taylor expansion of the exponential, and so the conclusion is that my centrality score is exactly given by the diagonal entries of the exponential of the adjacency matrix. Okay, so the score of the ith node is the ith diagonal entry of the exponential of A. I see 2 questions. So how does centrality relate to the steady state distribution of the corresponding Markov chain? Okay, so steady state distribution should be given by the degrees, right, of the nodes. So it's not exactly the same. It's a correction of that. Okay, you can look at it as a correction on a degree. It's a different measure. By degrees, I mean the number of nodes related to, adjacent to each node they consider. Do you mean how the node influence the scale pattern for Frobenius? So you mean the dominant vector? Okay, so yes. So as we said, there are many ways of defining subgraph centrality, the importance of nodes. And one of these relies on the definition of a stochastic matrix associated with our graph, which could be a rescaled version of our matrix. So we could, for instance, normalize each row and get a stochastic matrix. This is what Google does, for instance. And at least in the original algorithm, we don't know what Google does nowadays. And what we obtain is a stochastic matrix. And with some extra hypothesis, we can assume that the Perron-Frobenius theorem applies. So that we have maximum eigenvalue that is 1, that is simple, and it's associated, therefore dominant eigenvectors are positive, and we can take the entries of this vector, of this eigenvector, as centrality scores. So I suppose this is what was meant in the question. And yes, this is a centrality measure, and it's indeed related to to other measures defined as matrix functions. It's not the same. There's actually a nice paper by Baines and Klimko that studies, so I'm not sure what the year was, 2000, maybe 13, I'm not sure. That does a comprehensive study of how these different centrality measures are related to each other and how one can vary some parameters to go from one to the other. So there are centrality measures of this kind. There are centrality measures defined using the Perron-Frobenius eigenvector. There are other centrality measures defined by the degrees, or the so-called Katz centrality measures, and so on and so forth. So it's possible to establish a relation between this, but in principle, this one is different. It's not the same as the Perron-Frobenius eigenvector. Okay, then of course one can go into details, but these authors have studied this problem and with care. Then again, there are many possible choices for centrality, and actually it's hard to say which is best. It really depends on what you want to compute, on the characteristics of your model, on what aspects you want to emphasize, and what aspects you don't want to emphasize, and so on and so forth. Yes. Okay, so all of this to say that the exponential of the adjacency matrix is useful in describing the properties of a network, of a graph. So what we have seen is that the diagonal entries give us the important score for nodes, at least in this model, in this interpretation. And if we look at the off-diagonal entries, well, clearly we can repeat the same argument, and we end up observing that the ijth entry of the exponential of A counts the number of walks with weights from node I to node J. So in some sense, it measures how easily information flows between these two nodes. And so it can be seen as a measure of communicability. Okay, so this was an application we had in mind, and I come back to this later to show a couple of numerical experiments. Now, let's go back to our decay bounds. So we'd like to characterize the decay behavior of functions of banded matrices. What kind of bounds do we want? So we start from a banded or more generally sparse matrix A. We choose a function such that f of A is well defined according to the definitions we saw, and we'd like to find bounds of this kind. So ideally, what we'd like to see is an exponential decay of the off-diagonal entries. So we'd like the absolute value of the ijth entry of B to decrease like the exponential of minus the difference between I and J. Okay. So here, K and alpha are positive constants, and we'd like these constants to be independent of the size of A, because in a nice case, think of matrices of the same type, but of increasing size. We'd like the decay rate to be the same. Otherwise, the bounds are not so effective. We cannot give a uniform truncation rule for obtaining a banded approximation. So what we'd like to have, and what is obtained in many cases, is this kind of results. Okay. Of course, these constants may depend on the function, and they may also depend on the spectral properties of the matrix A. And as an application to networks, if we have such bounds, this can help us identify nodes with low communicability. Because these a priori bounds are easy to compute. Once we have the constants K and alpha, it's easy to give an upper bound on the magnitude of diagonal entries. So if I minus J is large enough, so we're far away from the diagonal, large enough that this entry is smaller than a fixed tolerance, then I can say that the communicability between nodes I and J is negligible, right? Okay, so The problem of computing such bounds on the decay of functions of banded matrices has been examined by many authors. Usually, one of the papers that are most cited in this regards is the one by Demko, Moss, and Smith, who gave bounds for inverses of banded symmetric positive definite matrices. Okay, a similar analysis was also given by Jafar at the beginning of the 90s. And I have a slide on this later, but I'd like to say this right away. In studying inverses of banded matrices, one special place is occupied by the inverses of tridiagonal matrices and variations of this theme. There's really a lot of literature on this. There's a nice review paper by Gérard Morin, and there's also a nice paper by Jean-Pierre Dedieu, who also studied this problem and gave and described the behavior of inverses of tridiagonal block tridiagonal matrices with certain shift invariance properties. Then a generalization to general functions of banded matrices was given by Michele Renzi and Jean Golub, and this relies on polynomial approximations of functions. Then again, there have been many further developments. I'd like to take a quick look on how one can obtain such bounds. Of course, one can specialize bounds to matrices with special structures, okay? Or generalize to cases that go beyond usual Hermitian real complex matrices. For instance, one can have extensions to matrices with entries in C-star algebras. One can specialize approach to certain classes of functions that work well with certain transforms that can be used to characterize the bounds, and so on and so forth. The general idea, however, is to exploit suitable approximation of the function we want to compute. So the results we actually obtain are given in this theorem. So suppose we have, so this is perhaps a theorem that combines a certain simplicity in the hypothesis and a convincing result in the thesis. Then of course there are many versions of this. Suppose we have a real symmetric, banded, or otherwise sparse matrix, and suppose we have a smooth function defined on an interval contains a spectrum of A. So here we're working on a function with real spectrum, right? Sorry, on a matrix with a real spectrum, and so the function can just be defined on the real axis, on a segment containing the spectrum. Then we can compute constants C and lambda. C is positive, lambda is between 0 and 1. That depend on the function and on the spectral properties of the matrix A, such that in the banded case, the ijth entry of f of A in absolute value is bounded by, this is exactly the kind of exponential bound we were looking for, C times lambda to the power absolute value of I minus j of n. Okay? So we have an exponential decay of these entries, an exponential decay with respect to the distance from the main diagonal described by this I minus j. And as we can expect, the decay is faster if the bandwidth n is smaller, and it's slower if the bandwidth is larger, right? More generally, if we have a sparsity pattern that's not necessarily banded, what we can do is replace this exponent with a graph distance. So to our matrix, we can associate a graph, okay? So the number of nodes in the graph is the same as the size of the matrix, and there's a connection, there's an edge between two two nodes if and only if the corresponding entry ij, after labeling, the corresponding entry of the matrix is non-zero, right? So the inverse process with respect to the definition of the adjacency matrix. On this graph, we can define a distance, which is the number of edges in the shortest path that connects nodes I and j. And if we replace this exponent with the graph distance, we still have that the ijth entry of f of a is bounded in absolute value by c times lambda to the power d ij. Okay, so this more general version allows us to have decay bounds that really mimic the sparsity pattern of the matrix. Okay, so how can we apply this? If we want, for instance, to give bounds on graph communicability, in the banded case, we can just choose a threshold, a value communicability such that below that value, I'm saying there is no communication between nodes, the involved nodes. Then I look for the smallest integer, m hat, such that the bound with m hat is smaller than eta, and then we can truncate our function to this bandwidth, right, and ignore the entries that are outside the band. Okay. So if the bandwidth of A is independent of the size, then and we had suitable spectral properties for our matrices, then the truncation, the bandwidth of the truncated version is also independent of n. Okay. So in this case, the number of node pairs with non-negligible communicability grows linearly with n. Here's an example. Here I'm taking small world network. So what I'm following is so-called Watts-Strogatz model. More precisely, what I have here in this specific model is, so I have a few nodes, okay. I connect them like this, I form a ring. And then I add some shortcuts on this ring with probability 0.1. So for each pair of nodes with probability 0.1, I add or not an edge between those nodes. So I could have, say, a shortcut like this and another shortcut like this, for instance. And so if we look at the adjacency matrix for this model, we clearly see the tridiagonal structure that corresponds to the ring, okay? And then some extra dots in the off-diagonal part that correspond to the shortcuts, okay? This is called a small world model because typically the average distance between two nodes increases like the logarithm. So if we enlarge our network, we keep adding nodes with this rule, the average distance only grows like the logarithm of the number of nodes, meaning that the distance between two nodes is typically quite short with respect to the size of the matrix. In this sense, it's a small world, right? Well, we normalize the matrix. So the matrix in itself is not banded, so we can use its sparsity pattern, or we can reorder it. So I'm using here a standard reordering method, heuristic reordering method that's called reverse Cathel-McKee. And what I get after relabeling the nodes and applying a permutation on the adjacency matrix, like we said before, what I obtain is this banded structure, okay? So I can apply my bounds either to the banded form of the matrix or to the original sparsity pattern. So this is what the exponential of the reordered matrix looks like. You can clearly see the decay behavior, right? And this is what the decay bounds look like. So in black here, so here I have taken one row of the exponential of the adjacency matrix, the first row with it. So on the x-axis, I have the indices of the first row. So, and on the y-axis, I have the bounds and the exact values of the exponential. So what we're looking here in black, I have the values of the exponential on the first row, okay? And so we can clearly see that there's an there's a overall decay behavior, even though it's oscillating because of the sparsity pattern. Okay, this is the actual non-reordered shape. Okay, in red we have the bounds that follow sparsity pattern. Okay, and in blue I have the bound that uses the reordering. Okay, so we can see that we can follow much better the sparsity pattern, the decay, if we go to the length of computing the graph distances. But it can be expensive to compute the graph distances, so there's a trade-off one has to choose. Anyway, it's interesting to see how this bound works, how these bounds work, and how they can help us predict the behavior of, for instance, communicability. Okay. Okay, I won't go into the details of how these decay bounds are computed, but the main idea is that we want to have good polynomial approximations of our function. And really, this main idea can be condensed in two lines, computations. And if we look at the entry ij of f of a, okay, and we would like to give a bound on this quantity, what can we say? We take a polynomial approximation of our function f with a polynomial degree p. Now, if we apply a polynomial to a banded matrix, we're just looking at the banded case here. If we apply a polynomial to a banded matrix, we obtain again a banded matrix with a larger bandwidth. So the bandwidth for pk of a is k times n, k times the degree of the polynomial times the original bandwidth. Okay. So if I take ij far enough, the entry far enough from the main diagonal, and so I far enough from j, such that pk of a entry ij is 0, so such that we are outside this band. Okay, this is km. This is 2km. If I take ij here, okay, outside the band, this is 0. So we can happily subtract it from this expression, right? There's an equality here. At this point, I can say that this entry is bounded by the 2 norm of f of a minus pk of a. Okay? And now A is a Hermitian matrix. So I can just, when I look at the 2 norm, since the 2 norm is unitarily invariant, I can just look at what happens on the spectrum of A. So this sigma of A is a spectrum. And bound this 2 norm of the difference between f of a and pk of a as the maximum of f of x minus pk of x, where x varies over the eigenvalues of a, right? Okay. And so if pk is a good approximation in the infinite norm sense, a good best approximation, in the sense of best approximation of my function f on a segment containing the spectrum of the matrix, then this quantity is going to be small. And under suitable hypothesis, this quantity is going to decrease exponentially as k increases. That's the main idea. Okay. So ultimately, everything boils down to the fact that sufficiently regular functions, ideally analytic functions, have good polynomial approximations. So I can find polynomial approximations with approximation errors that decrease exponentially with respect to the degree of the approximation. Okay, so I suggest we skip this part, which is just more details on the computation of polynomial approximations. And I just want to mention, so here we had something about the tri-diagonal case, but just to conclude our discussion, I just want to mention a couple of properties that give a partial answer to the questions of whether functions of quasi-separable matrices are quasi-separable, which was Xavier's question. So as we said, the answer is no, but an approximate structure is retained. And so what does this mean? There are results that make this idea precise. Here's one example of such results. And this is taken by a paper by Stefano Massei and Leonardo Robol from 2017. This theorem, and in the same paper you can find different versions of this theorem. The theorem says the following thing. The statement is purposefully vague because the hypotheses are a little involved, so I'm trying to keep it simple. What I'm looking at as the main result here. So suppose we have a quasi-separable matrix of rank K, okay? And we also need some additional hypotheses on the spectrum, but these are reasonable hypotheses. Suppose we have a holomorphic function on the disk of center 0 and radius r, with r larger than 1. Then we compute, so suppose that f is well defined on A, okay, so among the hypotheses is also the fact that the spectrum must be in the in this disk. Then we compute f of A, and we look at f of diagonal blocks of f of A. So these off-diagonal blocks, generally speaking, do not have low rank, but they have approximately low rank. And how do we characterize, how do we make precise this notion of approximately low rank? We look at singular values, because singular values give us the distance from the nearest matrix with a rank corresponding to the index of the singular value. Okay. So the bound proved by Massei and Robol says that the L singular value of the off-diagonal block C in f of A is bounded by this exponential bounds, gamma times the exponential minus AL over K. So I won't give you the exact expressions of the quantities gamma and alpha. They're positive. They depend on F and on the spectral properties of A. What is interesting is that there is this exponential decay with respect to L. So as we take, as we ask ourselves, what is the distance of our block C from the nearest matrix of the same size and rank L, the answer is given by this fast decay. So this distance decreases very quickly. Okay, and of course, if the quasi-separability rank of the initial matrix is large, then this decay is slower. Okay. Whereas if the quasi-separability rank is smaller, then we have a fast decay. Okay. And so this property guarantees that there exists a quasi-separable approximant of f of A. And we can choose, depending on how well approximated we want the quasi-separable structure to be, we can choose what will be the quasi-separability ranks of the approximates, okay, using these bounds. Just to conclude, I mentioned that similar results also hold for solutions of matrix equations with quasi-separable coefficients. Okay, so if we have a Sylvester matrix equation like this is very much like the one we saw in the example before, where A, B, and C are quasi-separable matrices. Then again, under suitable hypothesis on the spectra of the coefficients, it turns out that the solution X has an approximate quasi-separable structure, meaning that if I take an off-diagonal block y from X, then there is a decay behavior in the singular values of y, and this decay behavior is of an exponential nature, where again, well, rho is a positive quantity that depends on the terms of the problem, the spectra of my matrices. And this decay goes with, so the exponential minus L, where L gives us, is related to the index of the singular values we're looking at. Okay, so again, I can find, for a fixed tolerance, I can find a quasi-separable approximate to the solution of such a differential equation. To the solution of such a matrix equation. So in this sense, the quasi-separable structure is approximately preserved. Okay, I'll finish here. Thank you for your attention.
Merci Paola. Merci beaucoup pour cet exposé, bravo. Peut-être s'il y a des questions, vous pouvez prendre le micro ou la caméra ou les deux et les poser directement. Il y a déjà eu pas mal de questions. Il y en a une dans le chat, non?
I don't see anything new.
Non, ça n'a pas l'air.
Thank you.
Bonjour.
Vas-y Bernard.
Je peux poser une question. Donc, tu as montré dans les expérimentations un comportement stable, des méthodes qui, pour ces matrices quasi séparables. Est-ce qu'il y a un gain en performance? Comment il se comporte en pratique? Comment ça se comporte si on exploite cette structure? Est-ce qu'on a un gain significatif?
Yes, so I'm answering English.
J'aurais dû les poser en anglais.
Yes, so what I showed are mainly experimental results, because concerning the stability, unfortunately, one drawback of quasi-separable structure is that it's often hard to prove theoretically stability results. Okay, so in practice, everything works well as we saw, but proving stability is a bit harder. So that's an open problem. As I see a question by Jean-Claude about open problems, this is one of the open problems, proving stability results for quasi-separable structure methods. Now, concerning improvements with respect to standard methods, the quick answer is that it's hard to see this in practice, because so far we only have what I showed you are results from prototype code written in MATLAB, and in MATLAB it's hard to see the difference, because you need to have a C or other implementation. Okay, so you cannot compete with built-in functions, but the complexity analysis clearly tells us that there is an improvement. There's an asymptotic improvement from n cubed to n squared for the solution with respect to usual solvers. And there is a non-asymptotic improvement in complexity with respect to other structure methods. So, sorry, the complexity is O of n. There's an improvement not in this O of n, but on the constant that's before the n, that's hidden in the big O, and this constant is halved. So,
you are saying there are no implementation of efficient solver?
I'm sorry, say that again?
So there are no implementation of solvers for this, which have the good complexity?
So there are no good implementations, meaning we only have the ones made for experiments like this. But a good solid implementation for this specific algorithm is not available. On the other hand, there's good implementation of variant of quasi-separable representation, that is that hierarchical off-diagonal low-rank structure I was talking about yesterday. And that's a MATLAB toolbox that's implemented properly, the one by Massey, Raubal, and Kresnet. But otherwise, for this specific problem, there is also a prototype in MATLAB, but no, shall we say, professionally made, or at least very well made implementation that can really compete with existing code. Yes. So that's something that would be interesting to do, but it hasn't been done so far. Yes.
Merci. Il y a peut-être une autre question dans le chat, Paola, sur le...
Okay, so Jean-Claude was asking if there are open problems. Yes, there are a lot of them. So one of these was about, I mentioned, was about proving stability. Actually, let me go back. I had a slide about some open questions. One thing I didn't mention, but I think is interesting, is can we revisit these decay bounds in terms of the quasi-separable representation or some other kind of representation? So can we exploit structure representations to characterize the decay bounds? What I'm thinking of is, if you remember how the quasi-separable representation works, it turns out that a typical quasi-separable representation has more or less this shape, right? So a typical entry is, as we said, a column vector times a few matrices times a row vector. Okay. Here, what I have is actually the inverse of a tridiagonal matrix. So these are all numbers. Now, if we manage to prove that the GIs and the HIs are uniformly bounded, and the BIs and the AIs are bounded and bounded by a quantity smaller than 1, then we automatically have an exponential decay, right? Because here we have the powers of these bounds that are smaller than 1. Okay, if we manage to show that these generators are uniformly bounded, and these matrices or these numbers are uniformly bounded by something that's smaller than 1, then this is basically our decay rate. Okay, you can clearly see here that in the structure of the quasi-separable form of this is a matrix inverse for a tridiagonal, the inverse of a tridiagonal matrix, which is quasi-separable. It must have the structure. And if we manage to prove that these entries here, these objects here, the AIs are smaller than 1 in absolute value, then we have the automatically have the decay bounds. So can we do this? It can be done for tridiagonal matrices, but it would be nice to generalize this result. And actually, for tridiagonal matrices, we can find bounds, new bounds that behave in a comparable way to the existing ones. But it could also be that the quasi-separable representation gives us new bounds that behave differently and manage to capture some behavior that you don't see otherwise with this kind of bounds based on polynomial approximation. You never know. Other questions? So this was a comparison. Okay. Other question, can we extend this idea to rapidly decaying quasi-separable matrices? So what I mean here is, if we start from a banded matrix and we compute the function of this banded matrix, we saw that there is a decay. But we can also, and this has also been studied in the literature, we can also start with a matrix that's not banded but has a fast decay and invert that or compute a function of that matrix. And this function will still have a fast decay, maybe not so fast as the previous matrix, but it can be characterized, this behavior. Can we extend this idea to quasi-separable matrices? So what can we say about functions of rapidly decaying quasi-separable matrices, and how can we characterize in terms of structural representation this decay behavior. And then, of course, it would be nice to apply such results to the efficient approximation of functions of quasi-separable matrices, functions of abandoned matrices, and investigate possible additional structure in the generator. So I'm saying this either from a quasi-separable point of view or from others' point of view. Functions of banded and structured matrices are a topic of ongoing research for many researchers around the world. So that's mainly, these are the main avenues of research I can see in this moment. Okay. I see another question. Is it useful to calculate matrix functions of graph Laplacians? Oh, yes, absolutely. So we talked about only about adjacency matrices so far, but another matrix associated with graphs that gives us insight and behavior of the associated network is the Laplacian. Here as Laplacian, what is proposed is this, right? Although sometimes, well, for symmetric, for undirected graphs where the matrix is already symmetric, sometimes the Laplacian is defined as the matrix of degrees, the diagonal matrix of degrees minus the adjacency matrix, because it resembles a bit Laplacian for discretization of the Laplacian operator for grids, right? And yes, one can absolutely use functions of the Laplacians and also solve different differential equations with the Laplacian to describe dynamic behavior on the, for instance, diffusion or other kinds of behavior on the network. What is very, how to say, popular right now is the use of Laplacians, of graph Laplacians in the context of fractional partial differential equations on graphs. And there are, so you need to compute, for instance, say square roots of the Laplacians in this context. And there are efficient ways for doing this. And the results are interesting. There are also, you can also see unusual, unexpected, well, perhaps not unexpected, but let's say unusual with respect to what I just said, behavior like the so-called Levy flights. So these jumps across the graphs, which we usually don't see in the usual dynamic. There's a very recent paper in Journal of Complex Network by Benzi, Vrastante, Bertaccini, and Simonek, who investigate exactly this this behavior. So fractional differential equations on graphs, on network graphs with the Laplacian matrix. It's 2020, I think. Sorry, my writing is horrible.